Good morning. I am Mariusz Dąbrowski, the president of Jerzy Stelmach Eureka Foundation, which deals with interactive education and popularization of front-end scientific research. We gather active scientists and therefore for a couple of days offer you the lectures and debates under the project Science Closer to the Society. And this session is session number 5. We have had already the 4 other sessions devoted to other topics, for example, sports or medicine. And now we are dealing with the topic of classical and quantum black holes in the universe. Our project is co-financed by the Polish Ministry of Science and Higher Education under the Social Responsibility of Science program. Our session is held both in English and Polish, and all these pieces which are in English will be translated into Polish and placed on YouTube in a couple of days after this session. We have just heard the main lecture, just means 3 days ago, the main lecture given by Professor Klaus Kiefer from the University of Cologne, who will join us also today for the summary discussion. Hello, Klaus.
Hello, Mariusz. Nice to see you again.
And also, there was a talk yesterday by Professor Marek Biesiada from the National Center for Nuclear Research, Poland, Warsaw, Poland, who also joins us today. Hello, Marek.
Hello, good morning.
And also, we have another guest who is Professor Vincenzo Zalzano from the Szczecin Cosmology Group of the University of Szczecin. Hello, Vincenzo.
Hello, good morning.
Our last summary session is devoted to the topic with the title How to Practically Explore and Apply Black Holes and Other Strong Gravity in the Universe. We have experts, and so I will start with the provocative question, and this question will be the following. Can we, in fact, produce a black hole in the laboratory? Is it possible to produce a black hole in the laboratory of any size? I don't know, a banana, an orange, or a nut, or whatever, or maybe of the Earth size. I would like to ask first Professor Kiefer to comment on that.
Yeah, this is, of course, a very exciting question, and it was a hot topic 20 years ago before the LHC, the accelerator at CERN, started to run, because some people were concerned about that actually black holes were formed there and they could swallow the Earth, and that's the end. So this is a question of interest. And I would first, to summarize, all the calculations that were done showed that there's no harm. Yeah, so that even if black holes were created, probably they would not destroy anything, because high energies anyway, particles hit the moon, for example, and if black holes really were created, then you would have maybe already seen that on the moon. Now, what is the context of black holes? How could you create them? Standard black holes, those who are observed, which are observed, and we have heard about that during the week, they result from a collapse of a star, a star that has high enough mass. And of course, such black holes you cannot create in the laboratory because we don't have stars at our disposal. But you may imagine small black holes. But can you create small black holes? I mean, still you need a lot of energy. And people have speculated that maybe due to unknown physics, the energy scale where you can create black holes is actually not so high as we would think. This is a so-called Planck scale, which is very far remote and which you cannot directly generate at accelerators. I mentioned this in my talk. I mean, if you want to have a Planck mass particle, you would have to increase the accelerator to galactic sizes. But people have speculated, theoreticians, that actually our world has not only four space-time dimensions, but higher space-time dimensions, and that maybe some of these space-time higher dimensions are not as small as one would expect. Certainly smaller than to see in everyday life, but still big enough, say that with high energies in the Large Hadron Collider, you could probe them. So if this were true, if really there were higher dimensions, then energy is needed to create black holes in the laboratory would be lower. And in fact, you could, in principle, create them at accelerators. So 20 years ago, many people have done calculations and calculated cross sections. Of course, the result depends on these higher dimensions. And when the LHC was starting, when did it start? Maybe 15 years ago or something like that. I think the Higgs particle was discovered 2012, so it was a bit before, but nothing was found. Yeah? So all the results that we have seen with the highest energies available on Earth were consistent with no black holes. So to your provocative question, I would say yes, in principle, but it depends on unknown physics. It depends, for example, on whether the world has additional dimensions so that the energy scale, the Planck energy scale, is smaller than expected. But I'm confident that even if this is true, these dimensions have not the correct size to allow the generation of black holes on terrestrial accelerators. Of course, it could be that maybe due to cosmic rays in the universe, I mentioned the moon because I mean, in astrophysics, you can generate high energy protons and others, much higher than the energies in the accelerator, and they penetrate the universe and hit the moon, for example, or the Earth. And also there, no hint was found whatsoever that a black hole was formed. So it seems that, and I think these are other questions that Mariusz will then ask, it seems that we either have these big black holes that come from collapse of star after supernova had formed, or we may have very small black holes, microscopic black holes, primordial black holes from the early universe. I think that's a separate topic. No, you will ask.
Yes,
I could say
that's a
something.
separate. Yeah, that's a separate
That
topic.
isn't.
I
But
I
accelerators,
uh,
maybe Vincenzo or Marek or Mariusz can add something on the accelerators. But I would say that, yeah, it depends on exotic physics, and it seems that the world is not as exotic as some theorists thought. So I think we have no evidence whatsoever so far for black hole generation in a laboratory, although it's possible in principle.
Yes, I was dealing with the theories of brain universes.
Yes.
Actually, I showed some slides about it during my talk on Thursday. The idea is that there are extra dimensions to which, in which only gravitational force actually propagates, and not the other three fundamental interactions, nuclear, strong, weak, and electromagnetic. And due to this, gravity is somehow leaking into the extra dimensions. So somehow we cannot predict actually the gravitational force in our three dimensions. There can be some corrections to this. But as far as it was already mentioned, there were in this time there were topic of the Higgs particle in accelerators, also the topic of these extra dimensions, and also the so-called supersymmetric particles. And actually, it emerged that only the Higgs particle had become reality in the laboratories. The other two ideas, supersymmetric particles and extra dimensions, have not been then discovered. So they are not still discovered so far. So we cannot say anything about any curiosities. And if we rely on just Einstein's relativity, we shouldn't somehow be very much afraid of the black holes. I can pass the comment to maybe Marek Biesiada, if he doesn't mind. Because I heard a curious report from my colleague who from Kraków, it's south of Poland, where they constructed synchrotron, and somebody was asking them about the possibility to produce a black hole in this accelerating device, and we found it a bit, I would say, not appropriate at all, because it's a small device, not very high energies. And I think that it's nothing could happen, and Professor Kiefer already mentioned that to actually produce it without extra dimensions, we would need kind of a size of an accelerator of a galaxy. But anyway, but suppose that we are having a black hole of an orange size, how would it behave if it was like passing, covered by the horizon, passing through some Earth or any planet or whatever? Maybe this is kind of a theoretical speculation. Anyway, let me give the floor to Professor Biesiada, maybe to comment more on that. Is it dangerous to have black holes around or not?
Okay, so well, let me start. I mean, just with a few words regarding this fear about the producing of black holes in the laboratory. Yes, I mean, Professor Kiefer generously, I mean, invoked these exotic ideas with extra dimensions. I mean, classically, and without invoking them, it is even not so easy, not so possible, I mean, to think about it using the classical or standard theory. Well, maybe, I mean, telling about the energy scales would not be so appealed. I mean, I will appeal to the imagination of the audience by reminding that in order to have a black hole, the matter content should be compressed below the Schwarzschild radius. Now, and everybody can do make calculations. Even in the internet, there are calculations of Schwarzschild radius. You can put any number you like to calculate what comes out. So we've been talking how about the stars and galaxies, the realistic cases, but you may contemplate, I mean, would I be possible to make, not invoking synchrotron, to create a black hole in the garage, gather some stuff and compress it. Well, I mean, the recipe is simple. I mean, compress until it is hidden below the Schwarzschild radius. I have my Schwarzschild radius as well. Everything does, but it turns out that I mean the usual size object should be compressed to the trillion times smaller dimension than the electron in order to form a black hole. So you may now feel how ridiculous it is even to think that it could be possible with simple macroscopic objects. Uh, Things become more tricky if we go to the realm of particle physics, collisions, accelerators, and yes, well, indeed, there were some ideas, exotic, as already mentioned, that implied, seemingly implied such a possibility of producing again a particle size, minuscule black hole. And now the question is, as I understand, Mariusz, is it dangerous at all? I mean, so for example, I mean, is it dangerous to have a vicious particle around
To
a
make
drop?
it more provocative,
Yes.
some people say that this bolide in Siberia early this previous century was due to a small black hole or something like this.
Uh,
Okay.
well, I mean, my reaction to the bolide is like in with the line of thinking of Ockham. Do not multiply the entities unless unnecessary. So we didn't seen or have strong evidence of a black hole colliding with Earth, but we have plenty of evidence, and each August night you can see it that meteorites are falling down the Earth, and yeah, this is regarding this event. But you asked a very interesting question of what happens if the orange size, because it is not, well, to put it very clear, from the pure theory, mathematical theory of general relativity, there is no obstacle to have a black hole of any mass, right? I mean, this
Right,
theory
right.
does not forbid you. I mean, it is the physical realization of such a concept that it is hard to imagine, and well, perhaps when we are talking about physics, the statements are never so rigid as mathematical statements, so we should avoid the saying always or never. But it is extremely hard to imagine that we can manage this with a macroscopic object. But is it dangerous? Would it swallow the Earth, devour the Earth? Even if this Tunguska meteorite was a black hole, so what happened to her? I mean, just make the destruction, but what then? Uh, and it is an interesting question because during the previous discussions, we talked that uh, the way in which a black hole swallows the matter is through the accretion. We've been talking about the accretion disks because, well, in the binary systems, there are disks which are formed due to the angular momentum conservation demand. However, it is not the only type of the accretion. The original one, because accretion is understood as falling matter on the massive body. The first type of accretion contemplated in literature was so-called Bondi accretion, which was a radial accretion
Yes.
toward the center. And indeed, such cases are realized sometimes. For example, if the protostar is forming from the molecular cloud, this accretion is not in the form of disk yet. It is rather a radial Bondi
It's
accretion.
just like a free fall of a stone from,
Yes,
from the roof.
yes, yes.
It's
So
in
it's just
general, it's a bent
radially
trajectory,
falling.
but a piece of it is straight. So it's It's just radial,
Um,
yes.
and it is a condition for this Bondi accretion that in order to so let us imagine the massive body moving in the medium. It would accrete the medium which are within some sphere of influence. The expression is actually very similar to the expression of the Schwarzschild radius, with the difference that in the denominator, instead of the speed of light squared, is the local speed of sound squared. Anyway, it is not so that the object immersed in the medium will swallow everything up to infinity. I mean, there is some sphere of influence which make it working, right? And now it depends of how dense this environment is. Because and this is similar. We mentioned this yesterday, that people are afraid that the black holes are eating everything that surrounds them, but the truth is that it should be a sort of medium, and the downfalling through the innermost stable circular orbit is the mechanism which actually swallows. So, in other words, I mean, if the sun is replaced by the black hole, let us imagine that it happens instantaneously now. The Earth would continue to revolve around the same orbit for millions of years. It doesn't mean that this vacuum cleaner is placed in the center of the solar system and swallows everything at once, right? So to make
Except that we
story
would
short,
be frozen
yeah,
because there would not be the sunlight.
yes, of course. I mean, the consequences would be tragic, but not in the way that it would devour the Earth immediately. Just to the conclusion, to the point, it depends. So, for example, if you imagine, I mean, that in CERN, a black hole is created in the realm of particle physics, we should remind that, I mean, in the world of atom, if you look at the size of the atom is just a vacuum, emptiness. Between the first stable orbit of an electron is nothing, right? So even in these particles, if it is formed, it will be formed in the vacuum. It will never or it would be difficult for such a minuscule black hole to find an environment in which it can accrete onto this. Well, it could and should be calculated, but imagine that the black hole, mm, well, if imagine that the black hole hits the Earth, because the black hole does not have a
Yeah,
solid.
suppose that we have an orange
Yes,
size
around
black hole,
yes.
which is hitting the Earth as Tunguski bolide
Yeah, first
during.
of all, I wouldn't believe that this would work this way, like a
Mm,
meteor, because the meteor hits the atmosphere because it has a solid surface, and it there is a friction with the air, and
yes,
this friction is converted to heat, and so on and so on, and eventually it is heated up so much that it explodes and makes an explosion, etc. The black hole does not have a surface, right? It has an event horizon, but it is a pure geometry. There is no matter at all. I mean, this emptiness, vacuum. All
mm,
the matter responsible for this state of affairs is hidden below the horizon, right? So I would rather expect that this black hole will just smoothly go through the atmosphere without any
yes.
trace.
So
Go
like neutrinos,
like
which
neutrinos, yes.
actually go through Earth without any interaction. So a
Yes,
black hole could
exactly.
just go like this and nothing would happen.
Yes,
Yeah?
exactly. This is this is my understanding. And well, unless it is a Reiser-Nordstrom black hole which has electric charge, we should keep in mind that the reality around us is shaped by the second great fundamental force, which is an electromagnetic force. The way why we are functioning is the responsibility for this is due to electromagnetic force and its action. And what we are talking about, the friction, the heat, and so on, it mostly relies on this of the world being composed of electrically charged particles. I mean, gross. The gross charge is zero, right? But
Yes.
each and every particle has its charge, so it is very complicated, and therefore this world is so beautifully, I mean, diversified. And now to the point, the black hole will not have a charge, will not have a chance to electromagnetically interact, will not exert friction going through the atmosphere. The only way of acting to it would be gravity. What sort of gravity could the orange size black hole exert to the surrounding? This could be sort of accretion, and it depends of how fast it will travel. Will it have time to accumulate or to swallow due to accretion anything? Yeah, so it is an interesting question. I mean, some people have made such a calculations. For example, our colleagues from Warsaw, Marek Abramowicz, Michał Beger have calculated, I mean, or contemplated the existence of primordial black holes, and they made these calculations of the accretion that it could happen while this black hole could go through the neutron star. So you see, even a neutron star, the densest material configuration we know in nature, the neutron star is not obstacle for the black hole to just penetrate, go through it. However, the energy losing due to this Bondi accretion could make this black hole being captured gravitationally by this neutron star and eventually relax to rest in the center of it. And when it is in the center of it and the matter is very dense, then the story of swallowing can begin. But remember, in a dense environment, remember, this matter should be made to get closer than the than the innermost stable circular orbit of that black hole, etc., etc. Yeah, so I mean, the conclusion of their very interesting paper was that probably, yeah, with the caveat that they asked the question whether the primordial black holes could be responsible for the dark matter in our galaxy. Conclusion was no,
Okay,
because otherwise they would swallow the neutron stars, which we know they exist. Yeah, so
you
in short,
smoothly went into the topic of primordial black holes because in fact we have not yet defined what are the sizes of these black holes. Okay.
Can I
Yes.
add a curiosity on top of
Yes,
that?
please. Yes.
Because if the public does not believe us physicists, maybe they can believe Hollywood. Because
Yes.
I guess that everybody has watched nowadays Interstellar, the movie, no? So in Interstellar,
Not
there
in
is.
everybody, but yes.
Oh, that's bad. If someone has not watched it, he should watch it. But in Interstellar, there is a supermassive black hole named Gargantuan. Gargantuan is a character from a French book from the 15th or 17th century, and it was a giant.
Yes.
So it's a supermassive giant black hole located just after Saturn, and nothing happens. At least only to the people who go directly to it and enter in it, but all the rest is the same. Nothing has changed. And I want to add another curiosity on top of that. That if people are maybe believing, but that's just Hollywood pay attention because the director, Christopher Nolan, asked to a group of physicists to make calculations to make it the most realistic as possible. And among these people, there was Kip Thorne, which has won the Nobel Prize in 2017. So if in Interstellar, backed by physics calculations, we have a supermassive giant black hole close to Saturn, which is not very far from here, let's say, if it's our neighborhood, and nothing happens, then we can be safe. A blue hole of the size of an orange will do nothing.
But is it orbiting and rotating? I mean, it's a Kerr black hole or Schwarzschild black hole.
This I don't remember, and probably it was not very important for the plot of the movie. But I can check. I will check if it was a Kerr or not.
Yes. So in the meantime, let us come back to the problem of the primordial black holes. And it was mentioned already, an issue of dark matter. So what are these primordial black holes, and could they serve dark energy or dark matter? I can remind to the public that dark energy is the energy which in general makes the universe expanding with the acceleration, while dark matter is the matter which makes the rotation of galaxies to be faster than expected, because it's invisible, but gravitationally we somehow that we don't detect them, but gravitationally we think that there is some matter, some mass. So okay, primordial black holes, how do they form, and what can they serve? I don't know, Vincenzo or Klaus, I don't know who can start.
Sorry, I just wanted to correct myself because I remember wrong. Because in the solar system, there was just the entrance of this wormhole. Then Gargantuan was on the other side.
Okay.
So I'm sorry, I remember wrongly. So probably if there is a black hole of the size of the orange, something will happen.
Okay.
But with the black hole size of orange, I mean, these are speculations that a planet X, which is outside Pluto orbit, is a black hole. I cannot judge about observations, but I read in serious literature that some astronomers think there is an unknown planet, but there is no optical image or something, and there are speculation that it's actually a black hole of orange size that goes around the sun beyond Pluto orbit.
So this black hole could serve dark matter eventually?
This would be part of dark matter, yeah. I mean, that in the solar system, this would be, I mean, the size of orange. I mean, the Earth, if it was a black hole, would have this size of my thumb. And so it scales proportional with the mass. So maybe this orange, I have not calculated, but it's more like Saturn mass or something like that. And this would circulate around the sun, but only show gravitational effects, no other effects. So I'm not sure how sound these investigations are, but I think it's an option. And in principle, one could travel there. I mean, there are missions. There were missions to Pluto, and Charon, and I mean the moon of Pluto. And so in principle, that's not too far for a mission. So and then you could perhaps see whether or measure whether there is a black hole. But that's only a side remark to this orange sized black hole. I mean, by model
because
black holes,
I mean, this orange size is kind of easily adaptable by our mind. Okay,
that's also what the astronomers say. I mean, from measurements of gravitational perturbations at least I read, they conclude that this object, this unknown planet X, if it were a black hole from the Mars, it would have this size. So it's not just our imagination. I mean, that's what they say.
Yeah, we know that. I think Professor Biesiada had the plot during his talk. If one wanted the sun to be made a black hole, then the Schwarzschild radius, the radius, the horizon would be around 3 kilometers long. So it's not an orange size, but not very large, because 3 kilometers is a center of a town, maybe it's size of a town somewhere on the earth.
Yes.
But coming back maybe to what Professor Biesiada said during his talk, these primordial black holes, what are their sizes and masses? Are they of the size of these oranges or larger? What are these sizes? Can you remind us? They are of the I think of the size. Generally, mass is around the proportional to the mass of the sun, as far as I can remember. And
if I remember well, it's not. I mean, there is a quite large range for the availability of.
But the smallest one, I think, which is discovered, is this XTE J1650-500, which is in the Milky Way. I have some written material, so I can just say it's 3.8 times the mass of the sun. Okay, so it's generally these micro and mini black holes, which are sometimes also called quantum mechanical black holes, are smaller than the mass of the sun. So if they are smaller than the mass of the sun, then they are smaller than this 3 kilometer radius. So I think this famous orange black hole we are talking about must be kind of a I would say this is 3 kilometers, so say 1,000 or 10,000 smaller mass than mass of the sun, but still quite enough to be comparable to a planet on the Earth. So can we comment more maybe about these primordial black holes? Maybe somebody would like to add something curious about these primordial black holes. Okay, maybe let me put the question. Can they serve dark matter? Question number one. And the question number two, can they serve dark energy? Okay. First question, Enzo, maybe. Can they serve dark matter?
Yeah.
I guess that the point nowadays, I guess that the answer is no, because this is not my field, but as far as I remember something, for example, one of the ways in which they can, if they exist, measure possible primordial black holes is through gravitational lensing. Because if there is something passing in front of a star, the luminosity is dimming, and nowadays we can do, this is done routinely, we can calculate what is the mass of this object passing through. And as far as I remember, so far we have no evidence at all. I mean, we can put lower limits on what should be the mass if they exist. But as far as I remember, even if we were to assume that part of dark matter was made by primordial black holes, or even by black holes, even black holes, or other objects which are not luminous enough, we will not be able to explain all the dark matter which is there. So we will be able to explain a few percent probably. So I will tend to say that no, they cannot substitute for sure, they cannot explain all dark matter.
But they can contribute eventually.
They might, of course, because if you think about a black hole, dark matter is something which does not interact with light. We don't know how, by which process. We don't know which particles can do that. But if you think there is an analogy between black holes from which light cannot come and these dark matter particles. So some people are questioning and investigating if at least they could contribute. But as far as I remember, it's not a solution, meaning that if you're asking me, is dark matter made of black holes? I would say no. Maybe just a few percent, maybe, but that's not the solution, because then we are left with 99% of things which we don't know how to explain.
Okay, how about the dark energy? Can they be?
Well, so maybe I mean a few words.
Yes.
First of all, I just want to emphasize what already Vincenzo said. The dark matter is the problem of the budget, of the scale. We need 10 more mass in the galaxy than we can attribute to anything we see across the electromagnetic spectrum. So it is mainly the problem of this budget, the size of the problem. So if we are talking about dark matter as something which is non-luminous, non-observable, there are plenty of them. I mean, not so exotic as the black holes. I mean, the brown dwarfs, the planetesimals, planets, rocks in the space, but they don't, as Vincenzo said, are not able to explain all this discrepancy in mass that we need. Right? So this is just to emphasize it to the audience that, of course, they can be non-luminous, meaning the part of the dark matter, but by no means, and we have plenty of evidence that they cannot explain the all. A few words about the primordial black holes. I mean, this is interesting. I mean, their origin. The origin is in the early universe, when after the inflation, the scalar perturbations seeded the density anisotropy, which seeded the structure formation, the clusters of galaxies, the galaxies themselves. So it is the field of cosmology. We certainly don't have time to dwell on it in more details. However, I mean, there were the predictions which have been confined that the so-called the spectrum of these perturbations is uniform. I mean, at every scale you have a perturbation, right? And it might happen during this expansion that at every scale meaning every mass, I mean, the huge range of masses could have possibilities to collapse to a black hole. I will not go into the details because I mean there are some subtleties regarding the rate of the expansion. I mean the phase transitions can I mean cut some windows from this mass spectrum. However, this mass spectrum is really huge. From the rocks, planets, stars, galaxy size, and so on. Huge range of masses. In principle, it is possible. I mean, what was it realized by nature? We don't know. What we know, not in such an extent to be clearly detectable, clearly visible, or to explain the dark matter problem. That's what we know for sure. However, and this is interesting, why this orange size is on the agenda that we are talking about it. That in our observational tools, this is the size of the masses. I mean, these orange sizes, the planetary mass-sized primordial black holes, which are not yet accessible for our techniques to be detectable. So as Vincenzo mentioned, the gravitational lensing and especially micro lensing in our galaxy is restricting the abundance of compact massive objects which could contribute to the dark matter, but the performance of this method ends at some mass. In other words, I mean the planetary sized the massive body cannot be efficiently used as a micro lens, gravitational lens for us to observe. And therefore we have this window of opportunity in the sense that we don't yet have the tools to systematically study or probe the existence of such objects, right? So there are some other ideas put forward, like, for example, this what I mentioned, that if they were the dark matter, I mean, all the neutron star would have the seed who would destroy it during these billions of years of existence and so on.
Okay.
Other questions, dark energy, I mean, this is
Yes, dark energy, relatively shortly, because I still wanted to ask about extracting energy from the black holes.
Short and simple. Of course, no. It is a completely different phenomenon. By no means can be explained by black holes.
Okay, because they are playing just matter, more or less dust, which is pressureless, while for the dark energy we need something with negative pressure. And perhaps my presented objects like dark strings or dark brains eventually would extend some negative pressure, but they are in extra dimensions, so they are hypothetical. So
can I add very briefly to this, because I remember that we invited scientists for our cosmology group seminars, and actually there is a group of people mainly based in Hawaii who are pursuing the idea that dark energy it has been said, is let us say it's working like a sort of anti-gravity, no, because it has the total different behavior.
Yes.
And today's the most common idea is that this energy should be vacuum energy. Now these people have claimed that if we think about black holes as sort of balls of vacuum energy, then they should expand in the same way with the universe. And they have made some analysis, and they seem actually it's disputable, but I have seen that if you look at the masses of the black holes and then the sizes, they are growing proportionally to the expansion of the universe. So they are saying they might be, but this is just an idea, and there are many criticisms because still, how do you couple the expansion of the universe with the expansion of these objects? So that's very questionable.
Yeah, that's a hidden idea of having vacuum under the horizon, which is in fact related to this idea of black string, which can extend negative pressure. Okay, look, my colleagues, let me just turn into the last topic, which is also exciting, and I think the public would like it. Extracting energy from the black holes. Rotating black hole, Kerr black hole. There is this famous ergosphere, and there is this Penrose process. So can you maybe Klaus start saying something about in principle extracting energy from the black hole? Yeah. What you
Yes,
think?
as you already mentioned, this can only happen with a rotating black hole, not one that is static and Schwarzschild. And these rotating black holes, which have an angular momentum, they of course have the Schwarzschild radius that was already mentioned. And when you enter it, nothing can escape. But there's an interesting region outside the Schwarzschild radius, and this is only there for rotating black holes. And Mariusz mentioned the name, it's the ergosphere. The ergosphere. And the ergosphere is also something that is not so intuitive. It means that when you, as an observer, you enter the ergosphere, you can in principle escape. But when you're in the ergosphere, you have to co-rotate with it. I mean, you cannot escape rotation. The rotation of empty space-time, in a sense, due to Einstein's theory, is so strong that when you enter the ergosphere, you must co-rotate. Now, what has to do with extracting energy? So Penrose, I think when he prepared a lecture end of the 60s on that, on rotating black holes, he want to have something interesting for the students. And on the train to the university, he found this Penrose process that actually the ergosphere allows energy extraction. So you have a Gedanken experiment, a thought experiment, you have particles sent in, and you have a mechanism so that there's an explosion into two other particles, one that goes outward and one goes inside. And because of this space connection of space and time, that, I mean, the details are a bit longer, in the ergosphere, the result is that energy of the particle going down to the Schwarzschild radius can be negative, but overcompensated by, because energy is conserved, by the positive energy of something going outside. So you have, I mean, this inside the ergosphere, this explosion. So one goes outside with positive energy. This you can see because we are outside, and the other has negative energy and goes inside. Now, negative energy means it hits the black hole, but black hole has an energy, a mass. M is mc squared, so m is the mass, mc squared is the energy. So if you have something negative that penetrates the black hole, then you reduce the mass, no? Because mass is energy. And on the other hand, you have something going out that you observe as positive. So in this way, you can indirectly extract energy from the black hole. I mean, the energy is in the mass and we have nothing else. But you will see then in the calculations that the ergosphere by this will shrink and shrink, and at some point will vanish, and then you have just a Schwarzschild black hole and you cannot further extract energy. And you can calculate that, I'm not sure whether I exactly remember the number, but maybe 29% of the mass you could extract in this process, which is still very large. I mean, this is mc squared, so that is unimaginably large. So that's a theoretical process that Penrose has invented, and it's called Penrose process. The question is whether it's of relevance in nature. Of course, if we could maybe experiment with the black holes, we could perhaps use it, but it does not look like in the near future that we can do that. So it's maybe relevant only for astrophysics. And long ago, already in the 70s, was speculated that these huge energy outputs that you observe in so-called jets coming from active galaxies, and we assume in the center of these galaxies there are supermassive black holes, of course surrounded by accretion. We also have that, but you observe these jets with high energy, that this is in fact goes back to the Penrose process. It's called Blandford-Seneyek process by two astrophysicists, but and I'm not in the field of that, but I think it's not, maybe Marek can or Vincenzo can comment on that. I think it's not the unique way to explain the jet energies. It's one way, and I think it's not, to my knowledge at least, really clear that it's the Penrose process. But in principle, it could be, no? Ah, yeah, you see it. so
I
so
just
has,
display it behind me.
Very good, very efficient.
It was on stage yesterday too. So yes, Marek and Vincenzo kind of summarizing related to this extraction.
Yeah, can maybe add something on the astrophysics.
Yeah, Marek first, maybe. Can you comment more?
Definitely the Blandford-Seneyek process is the dominating explanation for the origin of jets. Yes, and as Klaus said, it is not exactly the Penrose process, unfortunately. It involves the magnetic fields and is which are anchored more in the or anchored in the accretion disk. So it extracts the rotational energy more from the disk than from the ergosphere itself. Indirectly, of course, I mean this is the extraction from the rotating black hole. But yes, it is true that it is not a direct and exact realization of the Penrose process, which is very smart. I mean, everybody who touched the general relativity immediately liked the Penrose process and the idea behind, but uh, we are upset that we won't be able to make the practical use of it.
Yes, but at least theoretically, we are on a good side. Vincenzo, how about you? What do you think about extracting
Well, I
energy?
have just two very short curiosities because what is behind me is a sort of structure. It's called Dyson sphere. I don't think it will work around a black hole, but it is built around a star. So it just take radiation heat from the star and converts in mechanical energy and things like this. And the last curiosity is that again, because I like to watch movies, and when I saw the topic, I immediately had this image. This is more for younger people because there is this series of movies from Marvel, and in one of them, the last probably, there was Thor, one of the characters. Thor is exactly the god from North, and he was standing in front of neutron star. The neutron star was closed inside a cage, and he had to open because they had to extract the energy. I don't know which energy, probably this uh, gamma rays which come out. I don't know. And he was standing in front of this cage, opening with his hot hands, and he was just hit by this energy, surviving, of course, because otherwise the Marvel movie will finish soon. But these ideas are, how to say, are more popular than one could think. They have been even used in a series of movies. So if it is possible, I don't know. Now for sure no, because we don't have the technology to do this. Maybe in future civilizations, yes, not now.
In future civilizations. Yes, so you inadvertently revealed the next topic for our last session of this cycle, which will be exactly the extraterrestrial civilizations, and it will happen in February 2025. We are scheduled for that. And this is the message also to our audience. I already welcome you to attend this session. We will have it also announced on our webpage, which is www.fundacja-eureka.edu.pl. And also we will be broadcasting on our YouTube channel. So I would like to thank you very much, our guests, for experts for participation in this fascinating trip through the universe, looking at black holes of any size. And I think this orange size black hole is somehow has become a kind of a icon of this session. We will remember it very strongly, I think. I would like also to say that and acknowledge the support from the Polish Ministry of Science and Higher Education to actually finance partially this session. and also the audience for watching us, both on Zoom and in particular on YouTube. And I wish you a very nice weekend, and see you during the next sessions. Stay tuned onto our activities. Thank you very much, my dear colleagues. Thank you very much, the audience. Goodbye.
Goodbye.
Thank you. Bye.
Thank you. Goodbye.
Bye.
Bye-bye.